Okay, class, this video is about signal detection theory. We're going to talk about why we use it, what it is, some definitions, and how it affects how we respond to sound. So one of the kind of foundational concepts within signal detection theory is called the response criterion. And the response criterion essentially is the listener's decision making. So the example I always use is when you're getting a hearing test. Sometimes you'll think you hear it, but you're not sure. What makes you respond? And at what level are you going to respond? Okay. So signal detection theory quantifies this decision-making process under conditions of noise or uncertainty. So when you're doing a hearing test, even though there's no physical noise in the environment, there's some what we call noise or uncertainty as to whether the signal is present. And so you can see the three different reasons, or what we consider this uncertainty or noise: the time pressure to make a decision. So like you're sitting there trying to decide yes or no. The relative intensity, so is it at a high level, low level? When signals get around threshold, there's a lot of uncertainty. And then you can also have some inherent physiological noise, meaning that there's just, some people, when they put the headphones on, they can hear their heartbeat and that sort of thing. So that's a potential noise source. So don't think of noise as like a physical noise in this discussion. And of course, the history is the World War II radar operators were trying to figure out, here's a big blip on this radar screen. Is it a bunch of birds? Is it a plane? Is it a warship? Is it an enemy warship? What is it? And so there's uncertainty involved in that. So you'll see in the videos that I sent as well, but here you have two distributions, and we're going to talk about probability. So the higher up on this graph, the higher the probability that you'll get a response at whatever level this is. So in this distribution, you have all noise, so there's no signal present. In this distribution, you have the signal plus noise. So remember, the noise, the uncertainty is always present. Okay, so if you picked a point along this distribution here there's a low probability that it'll be selected, and there's no noise. There's no signal in this distribution. Over here, if you were to pick this point, it's a high probability that it'll be selected, and the signal is present in this distribution. Okay. For those of you who have had stats, this should look very familiar, but this is the normal distribution. This is the bell curve. And essentially, if you take a task, you administer some kind of test or something across lots and lots of subjects, you will get a curve like this where you get 50% occur and perform around the mean. Then you have these standard deviations above and below the mean. And so this is a bell curve. So typically when I show students this, I'll show them that about 68% fall within plus or minus one standard deviation of the mean, and about 95, well, that'd be, about 95 fall within two standard deviations. So if you're doing an evaluation, let's say in the speech clinic, and somebody performs, let's say, two standard deviations below the mean, they're scoring over here. Okay. If they score two standard deviations above the mean, they're scoring over here. All right. And so you can see if they score over here, two standard deviations below the mean, everybody to the right of them scored better. Okay. And so this is what we use to quantify normal or disordered performance on standardized tests. And again, we'll go over this a bit more in class, but for now, I think it's important that you understand what the bell curve is, what the normal distribution is, what the mean means, what standard deviation means. Okay. So probability is easily calculated, right? So it's defined as the likelihood that an outcome will occur under specific conditions, okay? And can be expressed as a fraction or a decimal. which is then multiplied by 100 to get a percentage. So if you have a coin, a true coin with a heads and a tails, 1 over 2 or 0.5 times 100 gives you 50%. So your chance of obtaining heads with a true coin is 50%, tails is 50%. If you're doing a study where you want to, you have 6 different vowels that you're asking people to identify, and they have a screen and they hear a sound and they have to pick which vowel it is, and let's say there's 6 of them, you take 1 divided by 6, it gives you 0.17 times 100 gives you 17%. So the probability that they will just guess and get that right is 17%. So every time there is a presentation of a vowel, let's say in that example, there's a 17% chance that it will be correct. Okay? That's probability. So when we look at the distribution, again, they talk more in detail about this in the video, but when we look at the 2 distributions, remember this one here does not include the signal. This one here includes the signal and then any kind of noise or uncertainty associated with it. So when a task is very hard, let's say I presented a tone that was right by somebody's threshold, okay, like barely audible to them. Let's use that as an example. You'll see a lot of overlap in these responses because the task is difficult, and there's times where they're like, I think I hear it, so I'm going to push the button, or I'm not sure, so let me push the button anyway. So whenever the task is difficult, we call that a high noise condition, and that typically is shown by a lot of overlap between the no noise or the no signal and noise condition, and then the signal plus noise. So in this case, there's a lot of overlap. So this is a more difficult condition, all right? This down here, you can see there's very little overlap, right? So this condition's probably a bit easier, meaning that we're presenting tones that are well above threshold, and it's easy to tell if they're there. Okay, so we call this a high noise or high uncertainty condition, and this is a low noise or a low uncertainty condition. Now, when we're talking about different response types, okay, when we're looking for absolute thresholds, we're looking for 50% or greater, right? So there's going to be a lot of uncertainty when you're looking for what we call absolute thresholds, like we do in a hearing test. And because of that uncertainty, you'll have different types of responses. You'll have hits, which are true positive, which mean the person, the sound was presented and they responded. That's a hit. Okay. You'll have misses, which is a false negative, meaning that the sound was presented and they didn't respond. They missed it. You'll have correct rejections when there is no sound and there is no response, right? That's a correct rejection. There is no sound, there is no response. It's a true negative. And then you'll have false alarms, which are false positives. So the person's listening, there's no sound, but they respond positively as if there is a sound. So that's a false alarm or a false positive. And all of these types of responses make up signal detection theory. It's the relative amount of these responses that creates all of the information, all the statistics with signal detection theory. Again, I just gave you these examples, but let's do it one more time. A hit is when there is a correct response when the stimulus is present, okay? A miss is when the stimulus is present and there's no response. So you can think of, like, we use this also for like cancer screenings. You don't want to miss. You don't want there to be cancer and the test miss that the presence of cancer, right? So we always use hearing as examples, but this can be used for any kind of screening measure, any kind of test that you take for healthcare, cholesterol, whatever. It doesn't matter, okay? So misses are bad, especially when it's a very serious condition. Correct rejection is when there is no stimuli or no condition and they do not respond. And then the false alarm is when they're responding too much, when the present signal is not there. Now, in the video that I sent you, they talk about this criterion response, which this on the x-axis is the internal response, meaning that when I'm going to say yes or no. So if it's over here, I'm saying yes, there's a response to very low level sounds, if you will, mid-level, and then it takes a lot more intensity, or the level has to be higher for me to say yes, there's something there. Okay, that's the criterion response, and this black bar moves around a lot. Okay, but let's look at these two distributions. If you remember, this one, there is no signal. This one has the signal. Okay, and we, in the text that I'm writing, we broke it down into two figures, this one and this one, because sometimes they put all of this in one figure, and I think it's too hard to see. So let's do this. This is the criterion response. So at this level, this person says yes to everything above or no to anything below, softer. So when we look at this distribution, this is the signal distribution. When they say yes to everything above, these are all hits, meaning that, hey, there is a sound, and they said yes. These are all misses because they come from the signal distribution. So they said no, there is nothing there, right? Do you see that? So everything to the right is a hit, everything to the left is a miss, okay? So you can see somebody who has a criterion response about right here, right? They say yes, and they get a lot of hits, okay? They have a little bit of misses, but not too bad. Here's the criterion response for this distribution, which is the no signal or noise distribution. So when they say yes to that, to the right, they're false alarms. So they said yes, there is no signal. To the left is they said no, and there is no signal. So these are the correct rejections. Okay? So again, we'll go over this in class, but and I think those other videos should be helpful. But let's see what happens when you shift the criterion response. And they'll go over this. There's a liberal response criterion, meaning that they're going to say yes a lot more because their internal response, they've judged, hey, I'm going to push this button, if it was a hearing test, a lot. So sound doesn't have to be very loud, but I'm gonna judge that it's there. So what happens when you shift that response to a more liberal criterion, you get a massive amount of hits, right? A lot of hits because you're saying yes a lot that the sound is there, okay? And you don't have very many misses because you're saying yes so much, okay? But what happens is when you do that, your false alarms go up tremendously because now you're saying yes a lot to when the signal is not there in that distribution. And you have very few correct rejections, right? So your false alarms go way up, okay? But so do your hits, okay? And later, next week, we'll go through what that means. Now, here's a conservative response criterion, right? So now, sorry, morning allergies. So now, what happens is they say no a lot, right? They're waiting until the sound is a certain loudness. So it's got to be like, okay, I'm really certain I heard this, and then they push the button. Well, what happens is their hits go down a lot, right? And they miss a lot of them, okay? Their correct rejections are high because they're not pushing the button a lot, and their false alarms are almost non-existent because they're waiting until it gets to a certain level, okay? So conservative response criterion, moving the response criterion up to be, oh, it has to be much louder, you reduce your hits, you have a lot of misses, you have a lot of correct rejections, which is good, and you don't have a lot of false alarms, but you have a lot of misses, and that's the negative side of using that response criterion, that conservative response criterion. So that's it. We'll go over this more in class, and I hope this is helpful.